Okay, in this short tutorial we are going to look at the sound field in a room. Okay, at any particular point in the room, the total sound field in the room is going to be made up of two components. One is what we call a direct field, which I'll just call the acronym LD, and the other one is going to be the reverberant field, which is RREV. The direct field is the sound field that's coming directly from the noise source, all right, without any interactions with any of the surfaces, whereas the reverberant level has already undergone reflections from the floor, the ceiling and the walls. So this is a component therefore that represents the reflected component in the room. The actual sum of these two can be quantified by this particular formula here. LW plus 10 log Q divided by 4 pi r squared plus 4 divided by a parameter called RC. So in this particular formula here, what we have, all right, is that this is sound power level. Okay, so this is basically a property of the source only. It doesn't actually is determined by anything else. This first term in the log function here is what we call a direct field component, and the second component is your reverberant field component. Looking at this in particular in a bit more detail, the Q over 4 pi r squared, Q is the directivity of the source, so that's determined by the position of the source, whether it's actually on the ground, whether it's up against the floor on the wall, or whether it's sitting in the corner. So this value of Q can have a range of values of 1, 2, 4 and 8. 1 will represent a value where the source is suspended in free space without any other surfaces close by. The R term there is simply the distance away from the source. So for the direct field therefore, the two determining factors is the position of the source and also the distance away from the source. The other term is this 4 over RC. Now the 4 over RC term only has one particular unknown term, and it's RC. And RC is called the room constant. Now bear in mind that this represents the reverberant field, and the reflected field is obviously going to be dependent upon the characteristics of the surfaces of the room. So it's not surprising to find that RC can be determined from the mean absorption coefficient times the surface area of the room divided by 1 minus alpha. So in other words, the room constant is determined by the mean absorption coefficient of the surfaces and the surface area. So this is almost like an absorption term. There is a situation in all spaces that if you have a sound source in position and you take noise measurements as you come further away, you will soon come to what is known as the reverberant field. What that means is that the reverberant field will then dominate in that space. The cut-off point whereby the direct field is equivalent to the reverberant field is a situation where we've got these two terms equal to each other. And this particular parameter here, the R value here, then becomes a new term. This becomes something called the room radius. So I'm going to give that a subscript, okay, of little r. So this is only in a situation where we've got equality between the direct and reverberant field. All right, and that is actually an important parameter. So it tells you therefore when we go into the reverberant field, when these parameters here will then govern really the way in which the acoustics behaves in that space. One of the mathematical things that we need to do often is to work out the room radius. So taking this formula as it is here, we have to rearrange it for little r. Best thing to do is to take the r squared term up to the top here. So that becomes little r all squared. Okay, we can leave the q where it is, that doesn't change. We can take the RC across to the side, it comes to the top. The 4 pi can stay where it is. We can take the 4 down from the top here to the bottom, that's times 4. So this becomes 16 pi. So basically the room radius, therefore, in this situation is simply going to be the square root. Okay, so we can get rid of the square term by square rooting both sides. The square root of a square term is simply the term, and this becomes Q over RC over 16 pi. So again, with all formulas in acoustics, we need to look at the terms to actually understand what the room radius will depend upon. 16 pi doesn't really change as a constant. It's two parameters that govern the room radius. Directionality of the source, okay, that to a certain extent is important, because if you look at these Q values here, all right, it's these values here that will have the more significant effect on the room radius, okay, it'll make it greater, okay, and RC there is obviously the absorption in the room. Okay, so that concludes the very short tutorial on room acoustics.